Good morning, everyone. So today we will again revisit eigenvalue analysis. So for the multi-degree freedom system, and we will try to solve one problem and try to see that how we can approach these things. Okay. So in the last class, if you see, we were actually try to making formulating the equation of motion. We have formulated the equation of motion, that how a multi-degree freedom system can be written. And we have also discussed what is the very quick way to write the stiffness matrix. I think using that you can just write it in a very fast manner. And then second, we have tried to see what is exactly like a meaning of the eigenvalue type thing, because we see that now the characteristics equation is no longer root over of k by m. That is little bit complicated, and there like both the masses and both the stiffness are started contributing in that. So that portion we have seen already here, and then we have also tried to see that how we can able to came up with that lambda value, means which is the eigen values and the eigenvectors of that system, and we were also discussing what is the meaning of it, and we will just continue from there. We just introduced that orthogonality point, but we have not discussed that in the much detail. So we will start doing it today, and we will try to see that how the things is actually happening. Okay. So you have a you have your mass matrix, mass into u double dot plus ku equal to force. That is the undamped system, undamped multi-degree freedom system. And if it is multi-degree freedom, then m is not a single value, it's a matrix. U is also a vector, and k is a vector, a matrix, and f is a vector. And if we are writing the damped equation, then it will become mu double dot cu dot plus ku equal to force. Okay. But here the c is really very complicated thing to identify, because there are several theories also for calculating the c, determining the c matrix. We will come into that, but in the later stage, because first we have to understand the basic things, what is going on, then we will come how to estimate the damping matrix, what are the different types of damping, and those things we will come later. Okay. So now if you see that we have to solve this equation, let's just take this equation and just assume that c is known to us. Okay. Then we will see like how to calculate the c matrix and all those things. So in that case, what we did in the last class, that we transferred the system u to some another system q. Okay, that we have transposed. Okay, so that phi is nothing but the eigen vector matrix. Eigenvector matrix means it is like a set of eigenvectors, like phi 1, phi 2, phi 3, like this one. That full thing is capital Pi. Agreed? So that is the eigenvector matrices. So each column of the eigenvector matrices corresponds to the eigenvector for that particular mode. Agreed? Very good. Please remember that is the columns are the eigenvector matrices, not the rows. If you write the EIG comment of the MATLAB in MATLAB, you will get it as the form of columns, not in the forms of row. That is very important thing, because you will end up with a n cross n matrix. So it is you may feel that okay, that row is also the same number and column is also the same number. So it is very difficult to identify which one is what. So please remember that columns are the eigenvectors, not the rows. Okay. And once you take and obviously like after that, if you take the transpose, then the rows will become, but that is the transpose matrix, not the normal one. Okay. So now if we put that change here, so it will become q into q double dot plus c into q dot plus k into phi into q, that is equal to f. Okay. because F we are not changing anything. F is F. F is the force applied on the each masses. We have just changed, instead of U we are just putting it terms of Q. Okay, and if I just try to see that what is the dimension of the U matrix, U is n cross 1, phi is n cross n, and Q is n cross 1. Okay, any doubt? Any doubt? No doubt. Very good. Now we can also pre-multiply this thing with the phi transpose. If I pre-multiply with the phi transpose, we will have this thing. Okay, phi transpose m phi into q double dot plus phi transpose c phi into q dot plus phi transpose k phi into q equal to phi transpose f. That we can get. Okay, I just pre-multiplied with the phi transpose. Now if you see, there is this term, this term, this term, this term. Okay, and what was my objective? We were discussing in the last class that your M matrix was a diagonal matrix. Okay, and K matrix is populated matrix. Now your aim is to go in such a system where your M and K, or means like maybe M star and K star matrix will become both diagonal. Means you don't want to lose the diagonality of the M matrix, and you want to bring the diagonality in the K matrix as well. So obviously K matrix will no longer remain K matrix. It will be definitely going to change, because and also M matrix will be changed. So let's assume you are having some sort of like a M star or maybe M bar and K bar matrix. That will also automatically become C bar. But we are not at all doing anything with the C bar matrix. C bar we just leave it now. We will see after that how to have C and all those things. So we will be somewhere like that, and that will be also F bar. Okay. So what will happen with the F bar? Check the dimension. Phi transpose is how much? What is the dimension of phi transpose? N cross n. What is the F? N cross 1. So phi transpose is n cross 1. Exactly. So it is also a force form, but it is in the new coordinate system, which is Q. Okay. Previously we were at U, now we are at Q. So F bar is the forces on the Q coordinate, not on the U coordinate, because you are changing everything to the U to Q. Okay, and you are anticipating that your K matrix, a K bar matrix, is diagonal matrix, and your M bar matrix is also diagonal matrix. Okay, very good. Now the point is where that this phi has a special type of property. So now if you see how this phi is looks like, so this phi is actually consist of phi 1, phi 2, phi 3, like this way up to phi n. So what will be the phi transpose? Phi transpose will be like phi 1, phi 2, phi 3, like this way, with everyone will be transposed also, because previously this was like this, now this will be like this. Make sense? Okay. Now if I try to find out this K bar, some number, maybe let's say I comma j, then what is the writing thing? Because that is like phi transpose K phi. How should we do that? So we have phi transpose, that is, so once we have that, we can also go in the other way, that is, we are maybe assuming that what happening if we are doing this, like phi r transpose m phi maybe if J with Q double dot plus phi R transpose C phi J Q. Yes, now if you see here, that is one important parameter I have to tell. This U if you see, so U is like a this type of thing, equal to, you have a phi, that is phi 1, phi 2, phi 3 like this, with Q. Q is again this way, Q1, Q2, Q3, Q4. Okay, good. Now how we are writing U? U is phi 1 times Q1 plus phi 2 times Q2 plus phi 3 times Q3. Agreed? Because if you see this one with this one with this one with this, will be just multiplied and added. Agreed? Good. Yes. So that is my Q. So I can able to write U like this way. So for just to try to see some particular elements, and then try to see that what is happening there. Okay, so now if you see that phi transpose this one, that is phi transpose K phi. So phi transpose K phi will become 0. But phi transpose K phi will not come anything. So phi R transpose K phi J, that will become 0. And therefore what will happen, your that full matrix will become a diagonal matrix. Okay, so first let's see how that thing comes. Okay, then we can go back and we will check. So let's say this is a, so this is like, we are just first taking like a mass m1 and then mass m2. We have two stiffnesses 100 and 10, we just specified. Then the mass matrix, so automatically it will be m1 m2. Then we have the stiffness matrix K1 plus K2 minus K2 minus K2 K2. So how the system looks like? 2 degree of freedom, 1 degree of freedom is actually fixed and another degree of freedom is just fixed. Okay, so simple thing. So you see that first line number 20, if you see that line number 20, we are solving it, the eigenvalue problem. So we just write eigenvectors comma eigenvalues equal to I k comma m. Okay, make sense? This is the way how to use the I comment. If you not asked that first portion, like for example, how to show that, maybe you can see it here. Yeah, so suppose if you, instead of doing these two like a eigenvectors comma eigenvalues, instead of writing these two argument, if you just wrote only eigenvalues equal to I, then it will just give only eigenvalues, not eigenvectors. Means if there is a single parameter output, then it will give only the eigenvalues, not the eigenvectors. Make sense? And then equal to I of k comma m. So it will gives you the eigenvalues and eigenvectors. Then what we have to do, eigenvalues, once we are getting that, eigenvalues are actually square of the natural frequency. Okay, because we see it is a lambda square, and once we are solving that differential that the quadratic equation, we solved it in terms of lambda square. We are obtaining the lambda square. So natural frequency is lambda with that lambda. So we have to calculate the lambda form. Okay, so omega equal to square root of I of lambda. So if you do that, that is I equal to 1 to size of these, then eigenvector, displacement normalized. Yeah, so that will give this. So let's try to first see up to the equation number 23 that how it is. So if I just make this portion zoom up, so you can see first that eigenvalues, sorry, eigenvalues, come on. So eigenvalues, if you see, you will get two eigenvalues. One is 8.8 and another is 37.86. Okay. And you see, this is the diagonal matrix, eigenvalues. Okay, let's see what about eigenvectors. Eigenvectors, you see, that is something like minus 0.2326, 0.4931, and then again minus 0.3819, and then 0.3003. These were the eigenvectors are there. So what are the eigenvectors? Like suppose if I ask that, okay, what is the eigenvector corresponding to first mode? Yes, the first column, that is 0.2326 and 0.4931 with minus sign. Okay. Please do not go like a column wise, like first row wise, like 0.23 and then 0.3819. No, that is not the first eigenvector. Okay. It will be vertically upward. And eigenvalues are these two values also. Okay. Now what about the eigenvectors? Okay, eigenvector of that one. Okay. So this is okay. Now you can also able to see it is the omega. So you see, omegas are also calculated, like just we will take the square root of it. So we have used the command diag. If you see here, that diag command is used and then it is taking the square root. So what is the function of a diag command? Yeah, so it has a two function. If you are supplying a vector, it will make a diagonal matrix, or if you are inputting a diagonal matrix, it will make a array from that diagonals. Okay. So it will do the vice versa thing. You have to know that what you are supplying. Okay. Good. Now if you see that now you are coming that displacements we are checking, and first case is the normalization of the eigenvectors. And once we are normalizing the eigenvector, we are normalizing it in terms of displacement. So once we are doing the displacement normalization, we will see that that is coming eigenvector divided by maximum eigenvectors. Okay, so that is 1 comma I, that is the maximum number. Actually it should not be like 1 comma I, it should be max of eigenvector, so that it will just divide it with the maximum value whatever is coming. Okay, then so then what will happen? So now let's see eigenvector displacement normalize, how it look like. Then maybe the eigenvector displacement normalize, that is math normalize, that is displacement normalize. Yes, so now you see that that eigenvector which was like this, now you are trying to making one of them 1, means the top one you are making 1 and others you are checking. So you make the top one 1 and others is this. Okay, I will get like that. Huh? Actually it should be done with the maximum one. They have made little bit mistake, so that is actually should be done by the maximum one. So if you do it properly, then it will be like this: eigenvectors, and then you have to put here I will come into that one later. Okay, now let's see what about the eigenvectors look like. Now you see this, that also not happened. Oh, no. It is not only the max. It should be abs max. Okay, now you see, now your eigenvector was this, and now it get changed like this. Okay, so one is become minus one. Okay, no issue. That the, but you see that the both the maximum is amplitude is one. There is a one interesting thing if you try to notice in the eigenvectors. That is, first eigenvector has both the signs same. They are minus, and both of them are minus. But second one has minus, another has plus. Okay, so that automatically means that you will be in one case, you will be in, if you are in first quadrant, that means both are positive, or both are negative, means third quadrant. So first or third, your first eigenvector should be either in first quadrant or in third quadrant, because third quadrant is just the reflection of the first quadrant. If you multiply with the minus sign, it will be coming into the first quadrant only. Okay, and second one must be lying in second or fourth quadrant, because there cannot be any other possibilities, because one of them will be negative, and therefore either it will be in the first quadrant, or second quadrant, or it will be in the fourth quadrant. Okay, nice. Now if you also see, so that is one point. Now if you do, so the next step is that you do it, yeah, displacement normalized divided by square root of the this. So this is actually, let me show you. So here if you do phi transpose m phi, that will give something like m1, m2, m3, m4, like this way. So maybe with some bar. Okay, now if you see, try to see any of them. So obviously you can see that phi r transpose m phi j, that will be 0, and phi r transpose m phi r, that will be something m r. Okay, now if you are doing such a way that you are scaling the full thing, that you want a, so you have written that u equal to phi into q. Okay, so you are trying that this one you will scale up and down, and you will scale in such a manner that once you will multiply, this one will become 1. Means you are anticipating the phi should be such a way, means that will be maybe mass normalized phi. So maybe I'll just put it phi bar r. So phi bar r is such a manner that once you are dividing it, it will become 1. So what is the best way to do it? If you say that phi r bar equal to phi r divided by root over of m r bar, then what will happen? You see, phi r transpose and your anticipation is that. So give me one. Okay, So if you anticipating that, so now if you try to do that, what will happening? This is this m into this should be equal to phi r divided by root of mr bar into m into phi r divided by root of mr bar. Okay, so you are having phi r transpose m phi r divided by mr bar. Mr bar equal to nothing but this one. So phi r transpose m phi r divided by phi r transpose m phi r, that is equal to. So that is why you have to scale like this way to get a mass normalized mode shape. Make sense? Do you understand that? Why you have to divide it with the square root of that? Got that? Because that normalization is nothing but the scaling. You have to just scale that. Like displacement normalization is that maximum one should be 1. Otherwise, it is also like that. Okay. Okay. Good. So you see that is the way we have to get them this one. So here also, so we just followed the same procedure, that eigenvector mass normalized equal to eigenvector displacement normalized divided by square root of this. Okay, we will get the mass normalized eigenvector. So in case of the mass normalized eigenvectors, they are, means if we are calculating like phi transpose m phi, that will gives a identity matrix. We will not get anything else, we will just get an identity matrix. Okay, make sense? Good. Now, and you can also cross check that phi transpose m phi. So phi transpose m phi, what we have done? We have did that mass normalized eigenvectors mass normalized transpose into mass into eigenvector mass normalized. So what should be the phi transpose m phi? Phi transpose m phi should be 1. Yes, that is 1. If you see, that is 10 to the power minus 17. So these are there because of the numerical errors. Okay, if you do it analytically, you will get it exactly 0, but it is not analytically you are MATLAB is doing. MATLAB is using some of the solvers and all those things, so there some very minute number is present there, so that's why you are getting 10 to the power minus 17, but you can understand from the reality that that is nothing but 0. Okay, so once you do, these are the checks you have to apply. Like once you calculated the mass normalized eigenvector, you must able to get mass normalized eigenvector transpose mass again multiplied by eigenvectors should gives you identity matrix. If you are not getting identity matrix, that means there is some problem. Okay, and once it is the identity matrix, that means off diagonal terms are 0. Make sense? Very good. So now if we are again coming back here, so that happens with the mass. Okay, let's also cross check with the displacement as well, means the stiffness as well. They have not done the stiffness one. Let's do it. Okay, so what are you expecting? Identity matrix? No, we are expecting phi transpose k phi. So what should we expect? We can expect the eigenvalues. Look, now if you see phi transpose k phi, and previously your eigenvector, I think this one, look, they are same. Or if I just subtract these two things, like eigenvectors, eigenvalues minus phi t k phi. You see, is it 0? Because please check, previously there is a multiplication of 10 to the power minus 14. So come on, 10 to the power minus 14, if you are multiplying, it becomes 0 almost, nothing else. And then 0.7, 0.177, whatever the number is coming, that makes no sense. Okay, so we can see that once we are making the mass normalized eigenvectors, and we are using like mass normalized eigenvector into K matrix into again the eigenvector, it will give me back the eigenvalues. So if I just go back to my this calculation, or maybe I'll just do it first. That mu double dot plus cu dot plus ku equal to force. Now I have changed from u equal to phi into q. Now phi transpose phi q double dot plus phi transpose c phi q dot plus phi transpose k phi into u q should be equal to phi transpose f. Okay, now if I put phi instead of phi, if I put phi divided by, so if I put, so like let's say I'm using phi dash, that is equal to phi divided by root over of m bar. Okay, then it will convert it into mass normalized eigenvectors. Or if I just say that my phi is nothing but mass normalized, because this is nothing but the scale. You have phi 1, phi 2, phi 3, phi 4, you are just scaling them up and down, up and down. Okay, so this will be just like increased or decreased. But once whatever their product, they will be just scaling up and down except the zeros. Because zeros, if you scale up and down, it makes no sense. 0 multiplied with 10 will be 0 also, 0 multiplied with 100 will be 0 also. But if it is 1, then it will become 10 or it will become 100. So wherever you are getting the values, that will be scaled up and down. But zeros will not scale up and down. So if we are using this as a mass normalized eigenvectors, we can say that this one is nothing but my omega square. I wrote it omega like a capital omega just to indicate that this is a matrix. Okay, this is not a value, it's a matrix. Omega square. C, just I am leaving that. I'm not putting anything in that because that we have to discuss fully. That's a thorough discussion is required. And this one will become identity. Yes. Perfect. That will become identity matrix. We have just already checked that that will become identity matrix. So this, and then we will just thought like there is some of C into Q dot that will be equal to phi transpose F. Okay. Now, did we achieve our okay? So now if we forget C, so forget C. So then I will have Q double dot plus omega square Q equal to phi transpose F. Can I say that? Yes, I get it. Now, did I reach to my goal? That making the system diagonal. I think I reached. Because this is the diagonal matrix, I is the diagonal matrix. So, and this is a vector. Phi transpose F is a vector. It's not a matrix. It's a vector. Phi transpose F completely, because this is n cross n into n cross 1. So finally it will remain n cross 1. So it's a vector. So my system is now a diagonal system. And what is the beauty of that system? That system is completely uncoupled. So now just try to write it like, let's say, two equations. Okay, like a 2-degree freedom system. Just think like we have converted into this U, and now try to write it. So your system, or maybe we can just take that example problem also. So can anybody please note down what are the eigenvectors come and what are the eigenvalues come? Eigenvector displacement normalized. Sorry, not displacement normalized. That is the eigenvector mass normalized. Yeah, can you please note down the value? What is the eigenvector mass normalized? Just please note down the values. Eigenvector mass normalized. Okay, if you complete it, please let me know. Okay, then please note down the eigenvalues. Just two values, 8.88 and 37.86. Okay, and yeah, so yeah, so that is done. And now my system is, what is the mass and stiffness matrix? That is also important. So mass matrix is 5003. And my stiffness matrix is 150 minus 50 minus 50 50. Okay. So now if I try to rewrite, so my previous system was how much? 5003 with u1 double dot u2 double dot plus how much? 150 minus 50 minus 50 50 with u1 u2, that is equal to 0 0. Just because we are solving first the eigenvalues eigenvector. Now what I try to do, I try to go from u1 u2. So first yeah, so these two matrices we take the eigenvalues. So eigenval, so eigenvalues is coming how much? Eigenvalues 8.8 80, and this is 37.86. Okay, perfect. That is my omega square matrix. And eigenvectors are, so this is phi transpose normalized, mass normalized. Okay, so or maybe I'm just using phi transpose with a bar. Yeah, please tell the values in the column wise.
Yes.
Minus 0.2326. Okay,
Minus 0.493.
4931. Okay, then
Minus 0.3819.
0.3819. Okay, minus plus point
3003.
3003. Is that correctly written? Perfect, very good. So that is my phi transpose this. Okay. So now what I did first, I first try to change my u to a coordinate q, q1, q2 using this transformation. That is not phi transpose, that is phi only. That is minus 0.2326 and minus 0.4931 minus 0.3819 with 0.3003. Just this matrix I just substituted here. So what can I say also from that? u1 u2 is equal to, you can say, minus 2.3. I'm just not writing that many terms, I'm just writing the first two terms. Okay, minus 0.49 with q1 plus 0.38 and 0.3 with q2. Can I write that? Agreed? We can write that. Perfect. So good. Now think, we have converted it into this system, this equation. So what is this equation looks like? So that means this is changed to 1100 with q1 double dot q2 double dot plus 8.8 into 37.86 into q1 q2 equal to 0. Agreed? All of you agree with me? Very good. Now think, very simple. First equation can I write? q1 double dot equal to plus 8.8 q1 equal to 0. Can I say that? Everybody? Good. q2 double dot plus 37.86 into q2 equal to 0. Can I say that? What is the solution of the first one? Simple. This is a single degree freedom system. We have done so many classes on that. Okay, so we can just simply write it that q equal to a1 e to the power of lambda 1 t plus a2 e to the power lambda 2 t and q2 equal to, or here also not lambda 1 lambda 2, because lambda we also know that is its square root with the I actually. Yeah, so how it will be? It will be square root of 8.8. One with I, another with normal. Yeah. One with I and another with minus I. Plus minus I. Yeah. Plus minus I. So let's write it properly. That is I. What will be square root of 8.8? Please. 2.96. So I into 2.96 t plus a2 e to the power of minus I 2.96 t. Okay, or you can write c1 into cos 2.96 t plus c2 into sine 2.96 t. All are okay. Agreed? Next case. So that is, maybe I'm just using the 1 1, that is 2 1. Okay, so that is the first mode, and this is a12 I. How much is that? Just square root of 37, 6 point something. 37.86 square root 6 point, okay,
6.1.
6.15 t plus a 2 e to the power I 6.15 t, that will be c12 cos 6.15 t plus c22 sine 6.15 t. So we get both the values q1 and q2. Any doubt, by the way? Is it clear? Do you understand that how we solved and what was our strategy of solving that full thing and where we end up? Yes.
Q के बाद we have alpha prime.
Yes. Now you see, already this is the equation where you have to substitute. Exactly. Now you have q1 this, just you will substitute. I'm actually about to do that. To do that, yes. By that, before we substitute the q, any doubt? Any doubt? Anybody? Anything is coming in your mind? Okay, no issue. Very good. Now go and substitute. It would be very good if I can do it here. So my equation was u1 u2 with these values. So I can say this is phi 1, this is phi 2. I can say that because this is nothing but the phi 1, phi 1. This is nothing but phi 2. So phi 1. So phi 1 into. Now let's see this one carefully. That is, how can I write the q1? q1 I can write as e to the power of I lambda 1 t e to the power of minus I lambda 2 t, sorry, lambda 1 t into c11 c12. Okay, and the next one will be e to the power of I lambda 2t e to the power of I lambda 2t. Yes, that's it. So can I say this is e to the power of I lambda 1 t e to the power of minus I lambda 1 t e to the power of I lambda 2 t e to the power of sorry into c11 c12 plus e to the power of I lambda 2t into e to the power of minus I lambda 2t into c21 c22 with a phi 2. Phi 2 is here. I am just substituted the q2. c11, first one like c11, c21, c12, c22. So how many unknowns? Oh, exactly. Right. You are right. Yeah. Perfect. It should be A11, A12, 21. Sorry. So many mistakes. A11, A21, A12, A22. Okay. So what we can see? How many unknowns? 4 unknowns, exactly. Okay. Other things are unknown. What about the 5? So let's try to check what did we get and what are the unknowns. So these we have to calculate or known. U1, U2. U1, U2 we have to calculate. Simple. Okay. Now phi 1 is it known or unknown? Known. Once we know the system, phi 1 is known. Phi 2 is also known. E to the power of I lambda 1 t. Obviously, E is known, I is known, no question. Lambda 1 known. Lambda 2 also known for that system. Okay. So we know most of the things. What we don't know? U. And what about A1, A2, A21, A12, A22? Now remember, try to recall. For a single degree freedom system, how we solved the free vibration problem? Initial condition, exactly. So at initial condition, that means at t equal to 0, we know this value u1, u2. From there, we have to calculate that 4 value. Can we do that? From 2 value to calculate 4 value? Exactly, velocities are also there. So we don't have 2 values, we have 4 values. So from 4 values, we have to calculate the 4 unknowns. We can do that. So we know initially that thing. So we will know that A1, A11, A21, A21, A22. All the 4 values we got from the initial condition, and then we will start solving and we will finally get the solution. Make sense? Any doubt in that? Any doubt? Anybody? Okay. If you do not have any doubt, then try to think what we have done. That is mathematically correct. What is physically we have done? Perfect. We have divided into 2 single degree freedom systems. Where are the 2 single degree freedom systems? You are correct. Q1, Q2. That Q1, Q2 are the 2 single degree freedom systems. So now let's try to see what we have done it physically. So we had this system. So from here, we made 2 systems from a 1 system. Okay? Agreed? What is the mass of that first system? And what is the stiffness of the first system? Mass 1. And stiffness? Now see the beauty. This thing, once you are writing, that is in the mass normalized coordinate. It can be also like this. Means M1 bar, K1 bar, M2 bar, K2 bar. Makes sense? That M1 bar, K1 bar, M2 bar, K2 bar is just like 2 systems. once you are using a phi, any phi which is coming from as a eigenvalue, you will go here. You have seen that previously. Means if I am not dividing this thing, if I just only using the phi, I am going here in this frame. That is like any eigenvalues, means we are dividing it with any, means we are transforming to any eigenplane. Okay, and once we are coming here, we are actually using the mass normalized eigenvalues. That's the two difference. So here you can see the system itself is very simplified. It has a unit mass and its stiffness is nothing but the frequency square. Nothing almost. Okay. Now the question comes again, another question: where is that orthogonality of the modes? Where is that orthogonality? Because we are talking so many things on the orthogonality, that phi transpose m phi is equal to like phi r transpose m phi j equal to 0, and phi r transpose m phi r equal to some value, then phi r transpose k phi j equal to 0, and phi r transpose k phi r equal to omega square. But where is that realization? Try to think it, and please be very, very attentive. We are having two masses, okay, like these two masses are there. Now you can try to feel that these two masses are connected with each other by one spring, and it is also fixed with other thing. Okay, now you are trying to move to a particular set of coordinate system from where you are realizing that some connection is getting deteriorated, and you are changing that frame and try to go into that system. In that particular position you reach there where that inter-between connection is gone, and in all other values of phi you have that connection. You are maybe weakening that connection, and once you reach to that phi point, that connection is vanished. Again, if you not reaching that phi, instead of going to other values, again that connection will start acting. Just think like this way. Although this is like a full realization type thing, like you have another mass here, you have a connection like this. So you are making it like this way, that it is like this, and you have another mass like this. Okay, so you are going from one system to another system, so that your this spring is getting weakened up, and this spring is started formulating. So at one point of time you reached where this thing is exactly happened. Now if you again cross it, again you will have some mind link. So that is the point where your two systems become uncoupled, and you reach to a particular state from where if you solve one system and another system and superimpose them, you will get the original system back, because you came from that system via some transformation. Does that make sense? Sorry? Yeah. You see now that we calculated the phi, and rotation means that is the rotation in the space. If you see that, just let me come to that point. This rotation is the rotation in the space. Like for example, if you see, this one is the plot of that phi matrix, phi vectors, that the, so that axis is rotated. Now you are no longer working with the x and y axis, which was basically u, and you have changed it to u to q. How you go from u to q? You have to do some transformation, and transformation means it is a linear shift or translation. Means or rotation, means either it is translation or rotation. Now translation you are not doing primarily because then it is shifted, but you are making your axis point mostly same, and so you are basically rotating it. Okay, so once you have rotating that full thing, so you are going to some other axis. So I am telling that suppose instead of having it in this angle, if you are having it like somewhere here, then you are actually mapping it to a system where you have a spring, that one, and with some small link. You know, that link is not actually vanished. But at that point only, you will see that both the things are not coupled. Got that point? This is the realization of the eigenvectors, that how the eigenvectors looks like. And what I was telling from the first time that if you see that we are having the two axes or the two frame of references from where we are calculating it, like u1 u2, and now we are having q1 q2. So what was u1 u2 and what was q1 q2? Basis is a full mathematical term. If you try to say it more physical manner, obviously they are basis, no doubt on that, but
Is that coordinate?
coordinate systems little bit more fundamentally. So you can think that u1 u2 are the displacements of the two degree of freedom, but they were coupled. But you make another two single degree freedom system from that complicated system, whatever, and that two degree of freedom systems like the coordinate, or you can say that like, so these are become q1 q2, like this is q1 and this is q2. So from their motion you are predicting the motion of that main system. So these single degree freedom systems are your new axis. Did you get that point? Like what you are actually doing, like in this axis you are plotting q1, in this axis you are plotting q2, because this is a linear summation. So you take your this spring mass system, you are oscillating it, so you are getting some sort of oscillations in this direction, and you are also getting some sort of oscillations in this direction. So like oscillation in this direction means I should draw it like you are having some oscillation in this direction like this way, and you are having some oscillation in this direction like this way. So their linear superposition is coming somewhat in this type. Exactly, which is originally exactly. So that was something like your these two. So you are getting the solution there. Did you able to realize that, like what happened mathematically from the viewpoint of the physics?
U1,
Which one? U1 u2 are perpendicular, yeah. Or if they are not perpendicular also doesn't matter. No. That is, think it axis. Here also q1 q2 moving in the same direction. Direction is not the big deal. It is the system's parameter. So like suppose for example if you have a 3 degree freedom system, then you have to draw it in the 3D. Obviously, no? So then the direction is not exactly the thing. It is like a degree of freedom. So that means you have to think it like how many degree of freedoms are coming into picture. So that many number of axes it will be. U2 will be
0.
no, not 0. So that's why I draw it like an ellipse. No? It is not a straight line. I try to draw an ellipse actually. Because you never know whether it will be, where it will be. Because you see, it is a cos omega t sin omega t. So cos omega t sin omega t, it will make like a ellipse type thing. It is not a straight line. It could be straight line, u2 could be 0 also, or it could be like this way also, like fully u1 can also be 0. So when it's a ellipse actually. Okay, any doubt in that? Did you get that realization? And that realization only can be possible for the 2D way. It is very difficult to explain for the higher degree of freedom, because then visualizing it, it becomes very, very complicated. Like for example, if you think the 3D one, then like you have to think like a 3-axis is like u1, u2, u3, and then you go to some rotated one, that is q1, q2, q3, and then you have to do that whole thing. So instead of ellipse, it will become ellipsoid. After that, sorry, don't go. I cannot explain it. Okay, so that way you can do that. Yes, any question? Any question? Is that clear? You definitely will not get that realization in any book, no doubt. Because you have to read, definitely you can understand, but yeah. Okay, no problem. Now here, another very important point I have to say. That suppose we are not dealing with the 2-degree freedom. 2-degree freedom is just for the demonstration. Real life is not at all 2-degree of freedom. Yeah, most of the cases we can analyze from the 2-degree of freedom, but yeah, it's mostly meant for more complicated thing. So now, if we are going for like let's say 4, 5, 6, or like 100, 200 degree of freedom, and those who are designing like Parsoda and all those people, so they know that we are not considering all the modes. We are taking like first 2, 3 modes. So what are we doing actually? From that realization, can anybody please tell what are we doing really?
So if the mass multiplies,
Yeah, I am also coming into that. What is mass participation and how mass participation is coming into picture? I will coming into that point. But suppose if we try to feel that what is exactly happening, so we can think that we have that many number of axes, and if we really try to make a proper like a contribution, means proper transformation, we will be transforming it again to a n cross n number of degree of freedom system. But often this like ellipsoid type thing will be actually having very, very less contribution from some of the axes, and that contribution reduces with the mass participation factor. So once you are going for the higher modes, you will see those higher modes are really not contributing in your responses. So those axes you may forget. Means you have a higher dimensional space. From that higher dimensional space, you are mapping it to a lower dimensional space, and now you are solving the full system. Does it make some sense? That exactly we are doing there. Now I will derive and show that what is mass participation factor and how we should able to use that. Okay, after that, any question? Okay, nice. Okay, and also just another point, how these modes are orthogonal, because this response is not dependent on this response. Their response is completely different, and they are completely independent actually. None of them are dependent on each other. Simple. They are completely independent. So they are orthogonal. And orthogonality is achieved only when you can able to remove that spring. Okay. Good. So let's see how that mass participation factor comes. Okay. Now, if you think yes. So now, if you are not using the mass normalized mode, they are like a normal modes. Then what will happen? Just think you are not using the mass normalized mode, just using normal means eigenvalues and the eigenvectors. Then this one will be like, suppose you can write it mr qr double dot plus something with c, okay, plus c into qr dot plus something into kr into qr equal to phi. Now suppose if that is also like a rth value, rth row actually will come into that r. Okay. Or if is also a matrix, this is full matrix, rth one in the row. No, it was just coming with that one. Yes. So now what can I say? Okay. By the way, what is the dimension of that matrix, of that equation? Sure. This is 1. The 1 cross 1. Because MR, we just take only the single row. And we know that all other terms will be 0. So M will be diagonal, K will be diagonal. Okay. M R it is because we are not using the mass normalized, therefore it is not identity, has some values. Okay, but still it is diagonal because other term cannot be possible, like we are just scaling, so that term should be 0. Okay. So now you see what. So once we have dividing it this way, so let's see what is that f actually looks like. Like we have your some degree of freedom, so you will having f1, f2, f3 like this. So your f is basically written as f1, f2, f3 like this way, because they have to correspond with their respective eigen means respective degree of freedom. So f1 means it acting on the first degree of freedom, f2 will act in the second degree of freedom, third, fourth, like this way they are actually happening. So once we are doing that phi R transpose, that will be actually phi R transpose, not this, phi R transpose. So once we are doing it with the phi R transpose, this one, that means what will happen, that phi R into F1, F2, F3, F4, like these things are multiplying with each other. Make sense? And that is your phi R transpose, because phi R is normally a column vector and phi R transpose is a row vector. So they will be multiplied. So like this into this, this into this, this into this, this into this, like this way it will be substituted. So all added up and it will be placed there. So you will get this thing divided by MR. Okay. That factor is known as mass participation factor. Okay. So this is known as the gamma. So gamma is equal to phi R, gamma R, phi R transpose F divided by MR. Now maybe if you try to see it in the code, how it is written in the code, W, it is phi transpose, okay, yeah, that is the total mass, that is the modal mass ratio, which should be 100%. That is not that one, that is the modal participation factor. This is the mode participation factor, and that is the mass participation. Okay, so that two things are different. So if you see this thing, you can see that how much force is coming on that particular mode. Means we have already seen that this system is idealized with so many single layer freedom system. Now you have these forces F1, F2, F3, F4. They will be also converted into gamma 1, gamma 2, gamma 3, like this one. So that will tell the modal participation factor, that how much participations you can able to expect from each mode. Means how much the force is getting distributed also, you can say. So that way the modes are participating with each other. Look at that point. Okay. Then maybe we can close the session today here.